Okay, so this is part 2 of our discussion of chapter 1. So in the first part, we discuss the definition of a numerical methods, and uh, also we discuss some engineering practices and pace of problem solving, engineering problem solving, and we also discuss uh, accuracy and precision, and also significant figures. So in this video, this part 2 of chapter 1, so we will be talking about more about errors. So before we define an error, first I will discuss the major two forms or sources of errors. So we have here two major forms or source of errors, of numerical errors. So our errors in numerical methods. The first one, we call it the truncated error. And the other one is, we call it, this is the error due to round off error. So what's a truncated error? Truncated error, this is the result when approximations are used to represent exact mathematical procedures. This is due to approximations, approx of mathematical procedures, math procedures. So the error produced due to that, we call them a truncated error. How about a round off error? A round off error also because of approximation, but mainly because of the limited, due to limited significant figure. Due to limited significant figure are used to represent the exact numbers, and that error, because of that, we call it the round off error. It's due to rounding. So if we take an example here, so if I have an example, if x is equal to 178.299, this is the true value, this is the exact value. Now if one needs just 4 significant figure, so what are the errors due to truncation and due to rounding? So for truncated error due to truncation, it's possible that we have now a value equal to 178.2. It will cut off up to the 4 significant figure. It doesn't matter what's the number before that 2, as long as it's a 4 significant figure, then it will cut it off. That's truncation. That's why it's called truncation. So the absolute error now here will be around 0.99, or 9.9%. So later on I will discuss what's an absolute error. Now how about if we round this off? What will be the value of x when we round it up? So the value will be 178.3. So it matters. The number beside the last significant figure to the right matters because it's rounding. So if you remember the rules of rounding, so if the number to the right is less than or greater than or equal to 5, then you add 1, or if not, then just maintain it. So that's rounding off. And if we solve for the absolute error now for rounding is just 0.001. You subtract the true value and the rounding up value. So that's the difference between truncation and rounding. They're not the same error, but they are the same in sense that they are the result of approximation of some mathematical procedure. So now we can now define an error. What's an error? So we know the sources now of error. How about we define them? What is an error? So if you have a true value, or this is the exact value, true value, exact value. The true value is just equal to the approximate value, and plus the error. So because of approximating the true value, there's always an error included because of approximation. Now I will use symbol here. So I will use epsilon. For true value, I will use epsilon of t, or this will be called the true error. So what's the true error? There are different types of error. So true error, how do we solve for the true error? The true error will be equal to, from here, the true value minus the approximation. So the difference between these two, we call it the true error. And if you take it, take the absolute, then this one, we call it the absolute true error. True error. It doesn't matter if it's negative or positive, it's still an error. So we just take the absolute, and this will be equal to also the absolute true value minus approximation. So that is true error. Now, it's not good to define error in terms of true error, because, for example, I have here, I take a voltmeter, I measure some voltage, and if the measured value is, let's say, 23 volts, and the actual voltage, the true value, is 24 volts. So the true error here is just equal to 1 volt. So now, how about if I have, let's say, 3 volts. I measure at 3 volts, but the exact value is 4 volts. So what happens here? If we compare, it's the same true error, but let's just make it, let's just make this one 239 and this one 240, so that you can see the difference. What's the significant? And this one, para for you to appreciate error here, instead of 4, let's make it less than 4. If I have here 0.5 volts and the actual value is, let's say, 1.5 volts. Now if we compare them, what's the difference? They have the same true error, absolute true error, 1 volt and 1 volt, but what's the difference? In 239 and 240, it's fine to use a 239 volts for a 240 volt supply, but how about in a 1.5 volt supply? Is it okay to use 0.5 volts? Nope, it's not okay to use a 0.5 volts. Why? Because that's almost 1/3 of the original 1.5. You cannot do anything about that. So, although they have the same uh, true error, but the last example here is much worse than the first one. The first one, that's good, that's okay, 239, 240. The second one, it's very that's the worst measurement. 0.5 is not a good measurement if you're measuring a 1.5 volt power supply. So true error is not a good way to represent an error. So there's another one. We call it the true percent relative error, or simply relative error. This is much important compared to the true error. So I will use epsilon. I already use epsilon t here. So I'll just change this one. I will just make this one capital T to make it consistent. I will just make it consistent. So instead of epsilon here, I will be using E, just E. While here, I'll be using epsilon of T. So this represents a percent relative error. So what's the difference? This one is this is a true percent. There's also a true fractional. So in terms of fractional relative error. And to solve this one, this is just equal to the true error divided by the true value. We need to compare our error with our true value. So this is fractional. But for a percent, epsilon t, percent relative error, is just equal to, you just multiply it with 100. E divided by the true value, and we multiply it with 100%. So what is E here? Error, ET, that's the true error, or absolute error. You can make it absolute. So you need to know this one. This will be a very important concept when we try to solve some problems. So let's take an example. This one, I'll just copy it, then paste it here. Suppose that you have the task of measuring the voltage and current across a certain circuit and come up with 219 volts and 9 amps. If the true values are 220 volt and 10 amps, compute A, the true error, and B, the true percent relative error for each case. So, solution. So for letter A, let us solve for the true error. So how do we solve for the true error? First, for the voltage. What's the true error for the voltage? So true error, again, this is equal to the true value minus the measured or the approximate value. So what's the true value? The true value is 220 volts. What's the measured or approximate value? Is just equal to 219 volts. So what will be the true error? It's just equal to 1 volt. And for the current, what is the true error? It's a true value. True value is 10 amps. Then we need to subtract it with 9. That's the measured value. So therefore, the true error is also 1, but in terms of amps. Next, for letter B, how about the true percent relative error? Now, if you again observe this one, they have the same magnitude. It's 1 and 1, the same true value of the error. But how about the relative error? What's the difference between them? So for the voltage, the relative error epsilon of t will be equal to 1. That's the e of t, divided by the true value, which is 220 volts, and you just multiply this one with 100%. So the result will be equal to 0.45%. So this means there's an error of 0.45%. So it's less than 1% error. So this is a good measurement approximation. How about for the current? It's also 1 in value, 1 amps. But how about the relative error for current? How about the relative error? So the relative error now is of t will be equal to still 1, but instead of dividing it with 220 volts, we divide it with 10 amps. It's the true value, it's 10. Then you multiply it with 100%, and the result will be equal to 10%. So what does this mean? If you compare now the error between the current and the voltage, the error in the current is much higher compared to the voltage, even though they have the same value for the true error. So it's a must that we know the percent relative error instead of the true error. And actually, in reality, when we try to compute, we don't know the true value. It's when we solve problems, true values are always unknown. Of course, they are known. We solve them. We want to solve them. So how do we solve the error? So how do we solve the error if that's the case? Why do we need to know the true error? So there's another way of measuring error without knowing the true value. Although we still need to know the concept behind this true error. And that error, we call it the approximate error. Approximate percent relative error. So instead of the true, we don't know the true value, we use this one. So epsilon of A, meaning approximate relative error. So how do we solve this one? So to solve this one is just equal to epsilon A, approximate error is just equal to the current approximation minus the previous approximation divided by the current approximation. So what's this? What's the current approximation and the previous approximation? In numerical, we will be doing iterative calculation. So this means we have more than one approximation until we get to the the value that we want, the criterion or the pre-specified criterion or tolerance that we want. And so this will be our approximate error. Then what's the criterion? Because it's iterative, so there's a loop. We repeat again until we stop. And the stopping criterion, or we call it the pre-specified percent tolerance or criterion tolerance or criterion. This is our basis on when to stop our approximation. We call it epsilon s. Some books use stopping criterion. It's the same. And when do we stop? We stop when our absolute approximation is less than the stopping criterion or the pre-specified percent tolerance error. So if it's less than now the approximation, then we can now stop. But how do we know the value of this epsilon of s or the pre-specified? And usually when we approximate something, what the problem gives is at least give me the number of significant figures. Solve this one up to 5 significant figures. That's the problem. So it does not give the pre-specified percent. It gives the number of significant figures. That's why we discussed significant figures before. So to solve for the pre-specified, this will be the formula according to Scarborough 2019 book. It's equal to 0.5 times 10 raised to 2 minus n, and this will be in percent. And n here, so this is the stopping criterion. This is when we stop. And n here is the number of significant figure that we want. So it's based on the number of significant figures, not the pre-specified. Although we compare the approximate error and the pre-specified tolerance or criterion. So these are the different errors and stopping criterion. Now let's take an example, another example here. So for an example, we want to approximate the value of e raised to x. E raised to something. Approximate e raised to 0.5, e raised to 0.5 with in 3 significant figure. So you can use a calculator to solve this one, but we will not use your calculator, but we will use numerical analysis. We approximate it. So this is just an example, a very straightforward example. So before we solve that, we will be using this one, this series. We call this one the Maclaurin series expansion, e raised to x. It's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot plus up to x raised to n over n factorial. This is what we call the Maclaurin series expansion. So by increasing the number of terms of this one, we go closer and closer to the exact value. So the higher the number of terms, the higher the accuracy of our approximation. But the problem only wants us to have at least 3 significant figure that is accurate. So at least 3 significant figure. You can have more than that. So solution. So to solve this one, first we solve for the stopping criterion. So what will be our stopping criterion, or the pre-specified criterion, epsilon of s? So again, our formula is 0.5 times 10 raised to 2 minus n. What is our n? Our n is 3. Why? Because 3 is 3 significant figures. So this will be 2 minus 3. And this will be in percent. So to calculate this one, the answer will be 0.05%. So we stop our iteration when our approximate error is less than 0.05%. So this is our stopping criteria. So remember that. So we can now continue to solve for the approximate error. So first, let's consider the first one. E raised to x is equal to 1 plus x. So we only consider the first two, or if you want, the first one, we can consider the first term. That is just the first term. If we consider the first term, the answer here will be just equal to 1. E raised to, so e raised to 0.5 is equal to 1. So if we use only the first term. Now, if we want to solve for the true percent relative error, you can use your calculator to solve the actual value of e raised to 0.05. And actually the actual value or the true value is equal to, of e raised to 0.5 is equal to 1.68 648,721. So that's the true value. Now if we solve the true error here, it will be equal to 1.648721 minus 1, that's our first approximation, divided by 1.648721 times 100%, and this is equal to 9.02%. So this is still a very high error. So we don't use that approximation, it's equal to 1. So what we do is we add another term. So instead of just 1, we make e raised to x 1 plus x. So we need to add x. So to calculate this one, what will be e raised to 0.5? So e raised to 0.5 now will be 1 plus 0.5, where this is simply 1.5. So if we try to observe from 1, it becomes 1.5. So this will be our next approximation. Our first approximation is 1. That's the previous approximation. Our current approximation will be 1.5. So if we have now the previous and the current approximation, we can now solve for the approximate error, epsilon A. And that's equal to, the formula for that one is here, it's equal to the current minus the previous divided by the current. So what's the current approximation? The current approximation is 1.5. And we subtract the previous, which is this 1. And we divide it with the current, 1.5, and you multiply it with 100%. So the approximate error now will be 33.3%. Still far away with our stopping criterion of 0.05%. So we need to add another term. So that's the step of solving this one. Another way, instead of doing this one, we can also use tabular method. If we tabulate it in terms, with the number of terms, the result, we can also solve for the true error and the approximate error. So if we only consider the first term, So what will be the result? The result will be 1. This is 1 here. This is 1. So we put 1 here. And what's the true error? The true error is 9 point something, 9.02. Is it 9.02? Wait. It's not, this is wrong. It's not 9.02. This should be, it's not 9.02. It's 9.02 if it's 1.5. It's for the second term. So the value of the true error here will be 39.3%. So where is 9.02? 9.02 is during the second term. So here we have 39.3. So this is in percent. This is also in percent. At the first term, we don't have any approximate error because we don't have the previous approximation. It's the first approximation. We only have approximate error on the second term. So on the second term, this will be e raised to 1 plus x. So the result will be equal to 1.5. So this will be 1.5. And what will be the true error? The true error will be 9.02. So how do we solve that one? We solve it using this one, 1.648721 minus 1.5 divided by 1.648721 times 100. And the result will be 9.02. How about the approximate error? We solve it, that's 33.3. So here, 33.3%, and still greater than our stopping criterion, which is 0.05%. So next step will be you increase the number of terms. So if we increase the number of terms, what will happen? So we need to include x squared divided by 2 factorial, or simply 2. So what will be the result? This will be 1 plus x, so that's 0.5. So this is e raised to 0.5. Then we add another one, 0.5 squared divided by 2 factorial. So that's the result will be, including the third term, this will be equal to 1.625. It's 1.625. So if that is the result, if you want to solve for the true error, it will be 1.648721 minus that one, and the result will be 1.44%, and that's absolute. And for the approximate error will be, this will be equal to the previous, or the current, which is 1.625 minus the previous 1.5 divided by 1.625 times 100, and this is equal to 7.69%. So the approximate error goes down, so it goes closer to our stopping criterion, but still it's far ahead, 0.05%. So again, we need to add another term. So adding another term, so I just take 1.625 here. That's 1 plus 0.5 plus 0.5 squared divided by 2, and I add the another next term, which is x cubed over 3 factorial. So this will be 0.5 cubed divided by 3 factorial. What is 3 factorial? 3 times 2 times 1. So that's equal to 6. And the result here will be equal to 1.645833333. So 33333. So that's the result. Now if you solve for the true error, if you subtract it with 1.648721, then your true error will be equal to 0.175%. So the error now, true error, is less than 1. But that's not our stopping criterion. We look at the approximate error. So the approximate error will be 1.645833333 dot 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 minus the previous approximation, which is 1.625. 1.625 divided by 1.645833333 times 100, and this will be equal to 0. It's 1.27%. 1.27%. So it's still greater than our stopping criterion, which is 0.05. So we still need to add another term, the fifth term. So I'll just take the last term here, this one, I put it here, then I add it with 0.5 to the fourth over 4 factorial, and this will be equal to 1.64837. Then my true error will be, if we subtract this one with our actual value, it's almost identical, 721,837. The answer is 0.0172%. And for the approximate error, you do this again. I don't need to write it. It will be equal to 1.64837 minus 1.6458333 divided by 1.64837, and the answer here will be 0.158%, and it's still greater than 0.05%. So we need another term. So the sixth term now, we need to include the sixth term. So the sixth term now, this will be that 1.7, 0.5 raised to 4 over 4 factorial. So now this one here, and I add it with 0.5 raised to 5 divided by 5 factorial, and the answer will be 1.648697917, and the true error is now 0.0010142. So that's the true error. And for the approximate error, 1.648697917 minus 1.64837, the answer here is 0.0158%. Now if you compare with our stopping criterion, which is 0.05%, so we can now stop, because this will be this is less than 0.05% already. So we reach our stopping criteria. So therefore, our approximation for e raised to 0.5 now will be equal to this one, 1.648697917. So this will be our answer. Although I put here more than 3 significant figures, what it means is it should be accurate with 3 significant figures. So this one, and this one, 1.64. So if it's 1.64, our here is 1.648721. So it's accurate. We get 3 significant figure exactly. Actually, we also get the fourth one. It's 8 up to fourth one. And if you approximate this 1 to 7, we can also get that one. So there's a bonus of one significant figure. So that's the beauty of the formula of the stopping criterion. There's an allowance. It's not just the actual significant figure of the problem once, but it adds more significant figure. So okay siya. It's good. So this will be error, and you cannot appreciate it now because you can use your calculator to solve e raised to 0.5. Why do we need to use them? We need to use them because you need to know the concept behind the numerics, the engineering practices that I discussed, numerical methods and engineering practices. You need to know the concept behind these numerical methods. Now, the next thing that we will be doing will be to implement this numerical method, this technique, this iteration into a computer application. So we need to program this in our computer. We need to write a program. We don't want this type of solution. This is the pre-computer era. It's tedious. It has large number of arithmetic calculations. So if we program this one into a computer, then this problem now will be much shorter for us and more accurate. Depends on the stopping criterion that you want. So in our laboratory, our first experiment will be about this one. We will write a program. At least we will write a program that can approximate a value of a certain function. So if it's e, it's sine, cosine, or something, up to the number of significant figure that we will be telling the program. So if I tell it, give me e raised to 0.5 up to 6 significant figure, then your program should give me up to 6 accurate significant figure by using this algorithm. What we did here, this is actually an algorithm that we can transfer into computer program. Okay, so this will be the last part of chapter 1. The next part will be, we will be discussing this one into application. So see you at the next video.